Okay, so final remarks on so I can conclude that no information is lost when a signal is upsampled. So no information is lost when a signal is upsampled. Because we are introducing extra samples, we are not deleting any present sample. Okay, so the upsampler is a linear but not a time invariant system. And finally, the upsampler introduces spectral images. Okay, so this circuit, the upsampler combined with a low pass filter, this is called interpolator, and the process is called interpolation. So next we will consider reducing the sampling rate of signal xn, so that is called downsampling. And downsampling combined with filter is called decimation. Okay, so the downsampler is represented by the diagram. Signal xn given to a downsampler, which is reducing its sampling rate by a factor d and producing output yn. So if the frequency of input signal is fx and output signal is fy, then the sampling rate of yn is reduced and it will be given by fx by d. Okay, so let's take d equal to 2. So the system will be represented by xn downsampled by 2 producing yn, and let xn is defined by the sequence 7 3 5 2 9 6 and 4. So this is origin. Okay, so this represents x of 0. So I can draw this on a graph. So xn on y-axis and n on x-axis. And the instances are, this is 0, this will be -1, -2, this will be 1, 2, 3 and 4. So 0, 1, 2, 3 and 4, and on the negative side -1, -2. So at 0 the value is 5. Let's say this is 5. At 1 the value is 2. At 2 the value is 9. At 3 the value is 6. And at 4 the value is 4. At -1 the value is 3. And at -2 the value is 7. So this is Excel. And yn can be written as, so for d equal to 2 it will select one sample, it will reject one. So it will, if it will select 5, 2 will not be selected. The next sample that will be selected is 9. 6 will be rejected, 4 will be selected. And on the left hand side 3 will be rejected, 7 will be selected. And instances with respect to n will be, this will be 0, 1, 2, and this will be -1. So this means that what downsampler is doing, this is multiplying the signal xn with samples something like this. This is 1, at 1 the value is 0, at 2 the value is 1, at 3 the value is 0, at 4 the value is 1, at -1 the value is 0, and at -2 the value is 1. So xn multiplied by this time series, magnitude is 1, and the resultant signal will be yn. So at this point 1 into this value, this is 5. If this will be 0, this will be 1 into 9. This will be 0, this will be 1 into 4. And at this point the value will be 0. At this point 1 into 7, the value will be 7. Okay, so this will be 0, this will be 1 with respect to y, this will be 2, this will be -1. These are the instances with respect to y. Okay, so mathematically I can write yn is equal to x of 2n, and I can also represent this in this way, yn bracket downward arrow meaning downsampling by factor 2 xn. Okay, so we can represent this series xn and yn in Z transform also. So xz can be written as 7z square plus 3z plus 5 plus 2z inverse plus 9z raised to power -2 plus 6z minus 3 plus 4z minus 4, and yz can be written as 7z plus 5 plus 9z inverse plus 4z raised to minus 2. Okay, so now I want to represent yz in terms of xz. Okay, so unlike in upsampling, I cannot directly represent yz in terms of xz. Okay, so now if I put z equal to minus z in xz, so x of minus z, that will be 7z square minus 3z plus 5 minus 2z inverse plus 9z minus 2 plus 6z minus 3 plus 4z minus 4, and then I add xz plus x of minus z. So the result will be 2 into 7z square plus 3z and minus 3z will cancel out. 5 and 5, so I have already taken 2, so 5. 2z inverse minus 2z inverse will cancel out. 9z minus 2 plus 4z minus 4. Okay, so this is nothing but 2 into y of z square. Instead of z, put z square, so that will become 7z square plus 5 plus 9z minus 2 plus 4z minus 4. Okay, so xz plus x of minus z, that is 2 into y of z square. Okay, and z, instead of z I can write z under root z, so it will become y of z, that is equal to x of z raised to power 1 by 2 plus x of minus z raised to power 1 by 2 divided by 2. So we can derive Fourier transform just by putting z is equal to e raised to power j omega. So y of e j omega, that will be x of z raised to power 1 by 2 plus x of minus z raised to power 1 by 2 divided by 2. The value of z will be e raised to power j omega, and that is 1 by 2 x e raised to power j omega by 2 plus x e raised to power minus j omega by 2, and that is equal to x of half x of e raised to power j omega by 2 plus this term can be written as e raised to power x of e raised to power minus j pi dot e raised to power j omega by 2, and the result will be x of e raised to power j omega by 2 plus this can be written in the form e raised to power e of j omega by 2 minus pi. Okay, so if I use the notation y of f omega, that will be equal to y of ej omega, and x of f omega, that will be equal to x of eg omega. I can write the equation as y of f omega, that is equal to x of f omega by 2 plus x of f omega minus 2 pi by 2. Okay, so what we have derived, we have derived the Fourier transform of y, discrete time Fourier transform, and that can be derived from the input samples, that is xn downsampled by factor 2. Okay, so this is equal to half of x of f w by 2 plus x of f w minus 2 pi by 2. Okay, so x of f omega is periodic, this is periodic, and the time period is 2 pi, and x of f omega by 2 and x of f omega minus 2 pi by 2. They will be also periodic, but with a period of 4 pi, because 2 is in denominator. And the signal y of fw, that will also be periodic with period 2 pi. Okay, so how it will look? Okay, so considering the spectra of x of omega, we will draw spectra of x of omega by 2, x of omega minus 2 pi by 2, and we will add them, and the resultant spectra will be of y of omega. Okay, so now we will try to sketch the spectra of the output signal. Okay, so I have taken a imaginary band limited signal whose Fourier transform is known. Okay, and the Fourier transform of half of x of fw by 2 is given by this picture. The magnitude is reduced by half. Okay, and the frequency component are shifted by 2, and this is half of x of omega shifted by 2 pi, so this will shift to plus 2 and minus 2, and this is y of f omega. Okay, so you can notice that x of f omega is overlapping with its own spectrum, and this is called aliasing. And when aliasing occurs, the signal xn cannot be recovered. So how to avoid aliasing? Okay, so you can see that this spectrum of f of fw is spreading by a factor of 2, and this is a periodic spectrum with time period 2 pi. Okay, so if we make this spectrum 0 for mod of omega less than equal to pi and greater than equal to pi by 2, if we make this spectrum 0 for this value, by ensuring this, even if this spectrum is spreading by a factor of 2, the value in the range pi to 2 pi. Okay, so this is This spectrum is periodic with time period 4, with periodicity 4. So this will be 0 in this range, pi to 2 pi. Okay, and there will be then no overlapping. So the resulting spectra will be something like this. Okay, so this is x of f, this is x of f omega, and we have applied a low pass filter with cutoff frequency 1 by 2 for downsampling d equal to 2, and this is x of f omega by 2, which will be 0 after 1 by 2, and this will be shifted and filtered out accordingly, and the resulting spectra will be something like this. Okay, so this is not exactly like this. Okay, information is lost. It is evident that information is lost, but aliasing is not there, no interference is present. Okay, so that's why you have observed that whenever you are watching a high definition video in YouTube with a lower kbps value, so the picture quality is not that good because some information is lost. And whenever you try to watch any video using selecting a higher kbps value, so the picture quality is good because information is not lost in that case. Okay, so we cannot directly provide xn to the downsampler, we have to provide with it to the low pass filter, and then we can feed the output of low pass filter to the downsampler D. Okay, so let the output of this low pass filter is Vm. Okay, so in this case the frequency of sampling rate of xn is fx, sampling rate of vn will be also fx, and yn will be fy, that will be equal to fx by 2 for d equal to 2. Realizing xn will be given to a filter hn, and it will be given to a downsampler d producing output yn, and the cutoff frequency of hn will be pi by m radian, because of spectrum of xn will be spread by a factor this d. So this point onwards we want the value of x of f omega to be 0. Okay, so this downsampler will keep only m sample of x. Okay, and yn can be represented by this notation, and y of z is z transform of this, z transform downsampled by d xn, and this will be equal to 1 of d summation k equal to 0 to m minus 1 x of wk z1 by m, where w is e raised to power j 2 pi by m. So it is very easy to derive this, and y of f omega is discrete time Fourier transform of yn, that is downsample d xn, that is equal to 1 by m summation k equal to 0 to m minus 1 xf omega minus 2 pi k by m. Okay, so final remarks. Information is lost when a signal is downsampled. When signal is downsampled. Okay, so the downsampler is linear. But it is not a time invariant. And downsampler causes aliasing. Okay, so that's why you have to use